Most times when analyzing the area distribution of elements in the sample, you're really concerned with finding out where the compounds, alloys, or minerals are in the material. And one way of doing that with the electron maps is to overlay the electron maps and look for variations in color. Although this is a good indicator, it's really not very amenable to many real-world samples. In this particular sample, there's only 4 elements, so it's relatively straightforward to determine where most of the compound distributions are. However, in more complex materials with upwards of 6, 7, 8 elements in the field of view, that it becomes very, very complex to determine where the true compound distributions are within the area of analysis. To perform that, to perform a real confident compound analysis, you really would like to have some extra technique to do it. Because we have a full spectrum at each pixel location, we can apply statistical techniques to help us to analyze the large data cube of data and to have it interpret the data sets and to provide that information back. With the spectral imaging, what we have provided is a Camus analysis program, which is a statistical analysis program, that we can actually go and clear the periodic table and not use any information for that. Click the Camus analysis mode and enable it, and what the Camus will do is it will statistically analyze the data set and find all the pixel locations that have unique spectral fingerprints. So it will compare the spectrum of pixel 1 to the spectrum of pixel 2, determines if they are statistically similar or statistically different. If they are the same, they put those 2 pixels into one map. If they are different, it puts the second pixel into a second map. Then it builds up on a pixel by pixel basis all of the maps and all of the compounds in the material. So the result that comes out of this are a set of maps and spectra associated with each of the maps for each of the chemical phases that it finds within the material itself. So in this particular case, it has found there are 4 compounds, chemical compounds in the material, of which we have the component 1 is the speckled map that is displayed here in the upper left-hand one, and it has a distribution of elements in here which are high nickel aluminum content. We've seen that distribution before in the 2-phase material in the maps. The second component up on the right has an enrichment of the chromium and cobalt. That is a phase that we had also seen previously, so there's not too much surprise there that it found it. The 4th one, down the lower right-hand quadrant, is very, very similar to number 1. It has higher nickel and cobalt. It actually seems to be in that speckled region, so maybe the EDS is trying to pick out those individual particles that tend to be submicron. But it's trying to pull those out, even though the EDS really probably doesn't have enough spatial resolution to do that, but it is trying its darndest to get that to separate those out. But those are very, very similar. But what's interesting, most interesting in this particular analysis is this number 3 that's come up on the lower left-hand quadrant map, and the spectrum that comes up with that now comes up and it has a very tall yttrium component to it in these little faint regions. And if we overlap this map onto the image map, we can see that it is in these little vein regions. If we adjust the transmission or opacity of it, we can see that those regions are on the edges and what I like to call the webs between the globs on the image. And it shows us where all of these are at every pixel location in the sample. So these regions have a very enhanced yttrium content compared to the other nickel, cobalt, chromium, and aluminum contents within the material. If we do a phase analysis which binarizes these maps, we can then see that these maps, these regions, actually show up in the web regions between the samples.